Okay, so hello everybody. It's my honor to be here today to share about my research about the new acceleration methods for LASSO problem by using step elimination of variable. This research is a joint works with my supervisor Clement, Phương, and Cedric. In the first section, I'm going to introduce about the screening methods for LASSO problem. The motivation for LASSO problem is the so-called sparse linear inverse problem, in which we want to recover a sparse vector x0 from the noisy linear model that's B equal to A of x0 plus some noise. Here, the sparsity means that there are only some coordinates of the vector that are not zero. This problem play an important role in many application domains. For instance, the non-zero coefficient indicate the important column of A. This characteristic is equivalent to what we call feature selection in statistics. Another example is called the compressed sensing, since you can compress a very long vector into a new vector of extremely small size. And to solve this problem, there are many choices. One of the popular options is to use the convex penalization problem called LASSO. Here, LASSO is an abbreviation for the least absolute shrinkage selection operator. In LASSO problem, there are two parts. In the first part, we want to remove the noise by minimizing the distance between vector B and A of x by using the squares L2 norm, whereas in the second part, we encourage the sparsity in x using L1 norm. Here, the lambda is a parameter that controls the level of penalization. Since the problem is convex, a huge number of algorithms is available to solve this problem efficiently. However, solving this problem in high dimension is still very challenging. In the last decade, a new method called screening were introduced that allow you to solve the problem significantly faster. So what is a screening? It is just a method that can reduce the problem size by eliminating the zero entry of sparse vector. As a consequence, after screening, 11 column of A will be dropped. So we can only need to work with a reduced problem with smaller dimension. So there are two main benefits of screening. First, since the matrix becomes smaller, you can easily load it to the memory for calculation. Therefore, you can save a lot of memory. This is particularly important in large-scale application problem. The second advantage is that after screening, the second benefit is that after screening, you can quickly evaluate the matrix vector multiplication. Therefore, the screening procedure is often used to accelerate many solving algorithms with significantly improvement. So now, the crucial question is how to devise such a screening procedure. To do that, we need to introduce the duality problem of LASSO. By applying Fenchon-Rockefeller duality theorem, the dual problem that you obtain is just a maximizing problem of du, where u belong to dual feasible sets, say big U. If you take a careful look into the U, to maximize it, you just need to minimize the distance between B and U. So the dual problem is actually a projection problem from the vector B to the dual feasible set U. Here, we also introduce an important quantity called the dual gap, which is defined as the difference between the primal value Px and the dual value du. This dual gap is always non-negative and is only equal to 0 if x and u are optimal at the same time. Here, you can also establish the relation between x star and u star by KKT optimality condition. Here, you will have the inner product between the column I of A and U star will equal to some value belonging to the closed interval from minus lambda to lambda if x star I equal to 0. Otherwise, it will be equal to lambda times the sign of x star I. From this KKT condition, we can easily see that if the absolute value of this inner product is strictly smaller than lambda, then the first case must happen. That means that x star I should be 0. This is basically the screening rule. However, in practice, we don't know the exact value of u star, so it's necessary to have a more practical screening rules. To do this, u star can be replaced by an approximation that's a set containing u star here. Such a set is called a separation. In this way, instead of evaluating the exact value of the inner product, we may evaluating the supremum of the inner product. Here, we emphasize that the separation should satisfy the following three properties. First, it should be safe, meaning that u star must belong to that set. Second, it should be a simple geometric reason, so that the supremum can be computed easily. Finally, it should be as small as possible to best approximate u star. So how to choose a separation? Some popular geometry reasons are bone, half space, and a dome. Here, a dome is nothing but the intersection between a bone and a half space. Here, each bone can be identified with two parameters being its center and the radius. Similarly, a half space can also be parameterized by two parameters, that is the normal vector and the intercept. For the dome, it is parameterized by four parameters associated with the parameter of the corresponding bones and half space. In 2015, two separations were introduced called the gap bone and the gap dome that rely on the dual gap as you can see here. Note that both the regions are not only safe, but they also converge to u star since the radius of gap bone equal to the square root of two gaps that converge to 0. This is considered the state-of-the-art property that separates the separation from the other. In other words, we can say that the gap regions are safe simple and they are extremely small. Now, in this section, we would like to introduce our new separation called Honda dome. Our region is also safe, simple, and much smaller than gap dome. So how to build a Honda dome? We rely on a lemmas called the canonical representation of half space containing the dual feasible set. We saw that if U is a subset of a half space with normal vector G and the intercept L, then there exists some vector X such that G equal to AX and L equal to L is lower bounded by lambda L1 norm of X. On the one hand, U star belongs to U since it is the projection of B onto big U. On the other hand, you can choose L equal to lambda L1 norm of X. Therefore, we can say that U star belongs to this half space with L equal to lambda L1 norm of X. So now we can construct our Honda dome by taking the intersection of this half space with any other set bond region. Here we choose C and R at the center of and the radius in the definition of gap dome. Although the sadness of this half space is a direct consequence of the canonical representation lemma, we can also prove this sadness by using order inequality. That is the reason why we call it order dome. By the definition of order dome, we obtain a very nice theorem. The theorem contains two parts. In the first part, it's clear that U star belongs to the order dome. Due to the previous lemma, this is quite obvious due to the previous lemma. The second part is quite more interesting. That the order dome is actually a subset of gap dome. From this result, we can say that okay, our order dome is safe, simple, and much smaller than gap dome. So until now, we have seen that order dome is actually a subset of gap dome and all converge to U star. But how to quantify this conversion speed? This experiment and to partially answer this question. Here, let me talk a little bit about the setup. First, lambda is just a threshold of lambda max. Here, lambda max is just a threshold for lambda that is defined as the maximum of ATB. In this experiment, we consider three problems corresponding to different value of lambda, where lambda over lambda max equals to 0.8, 0.5, 0.3. For each problem, we plot the ratio between the radius of the dome and the radius of gap dome, as a function of dual gap. As you can see, when the dual gap gets smaller and smaller, the radius of the dome is just around 0.7 of the gap dome. For the next experiment, we consider a more complicated setup with 300 problem instance with two types of matrix called Gaussian and Toeplitz, and three values of lambda corresponding to the k, that's lambda over lambda max equals 0.3 for the top row, 0.5 for the middle, and 0.8 for the bottom. For each problem, we apply three solving methods by integrating the screening test into Fista algorithm, which is a standard solving method for LASSO problem. Its solving methods is also provided computational budgets, numbers of plotting operator. We then evaluate the empirical probability that the solving methods can solve the problem up to a precision. The results confirm that our order dome confirm that using our order dome instead of gap region may improve quite significantly the probability that the problem can be solved. So that's all. Here are some of the reference. The first one is the main reference about the gap region. The second one provides the KKT optimality condition for LASSO problem. In the last reference, the authors also provided a different technique and divide the same separation called the dynamic Savy dome, which can be proved to be equivalent to our order dome. So thank you.